Hello everyone. So today we're going to be solving problem 2.11 from the Griffiths textbook, and it wants us to use Gauss's law to find the electric field inside and outside of a spherical shell. So here we have our spherical shell, and it's with a radius r, and it has a surface charge density of sigma. And then later they want us to compare our solution to problem 2.7. So again, we're going to use Gauss's law. So I've written it here just so we can refer to it. And the first thing we're really going to have to calculate is this term E dot dA. So the integral of E dot dA, well, if you look at it, we have a circle here that we're trying to calculate, and it's at radius r. And because the direction doesn't really matter, like phi is the same in all directions, we can just simply write E times 4 pi r squared, and that will be good enough. So if you were in a first year course, this would be a good enough hand wavy explanation of how we get E dot dA. And if you wanted a more thorough explanation of how we get E dot dA, you would once again have to refer to the del in spherical coordinates chart and then do a multi-dimensional integration. So I am going to cover it now, just for those of you that want to understand how it comes from. But if you want to skip over this section, you're more than welcome to do so. Essentially what we do is we want to calculate this area here on the surface, and it's pointing in the r hat direction. So we're just going to write the area of that rectangle, which is r d theta times r sine theta d phi. And we're going to integrate E dot dA, so E r d theta, r sine theta d phi. And we do this because E is spherically symmetric. Again, if we calculate it in this direction, we'd get the same values if we calculate it in this direction and this direction. So we're exploiting the spherical symmetry here, so we can only do two integrals. So great. Writing this out now, we once again have E r squared sine theta d phi. Now, if you notice, E and r squared don't actually depend on theta or phi. So we're allowed to take them outside the integral. E r squared, integral of sine theta d phi. Two integrals, two values. So all we have to do now is to define the bounds of our integration so we can actually compute what the value of that area is. So if you notice here, this is theta, and it goes from 0 all the way down to pi. So theta goes from 0 to pi. And then we have phi, and phi goes from 0 all the way around the circle. So that's a full circle, that's 2 pi. So phi goes from 0 to 2 pi. So if you just do this integral, you get E r squared times 2 pi from the phi integral, and 2 from the sine theta integral, and that gives us E times 4 pi r squared. And once again, because we're working in the r hat direction, we get r hat. Great. So we've computed the value of E dot dA. And now we're going to try and compute the value of the enclosed charge. So first, looking at the blue case, we're looking at inside. If we zoom in and ignore the spherical shell here, there's actually no charge enclosed inside this big circle. So since there's nothing inside that circle, the charge enclosed is 0. And therefore, E times 4 pi r squared times r hat is equal to Q enclosed over epsilon naught, which is equal to 0. Now, we know that this will never be 0 and this will never be 0, And in general, r squared will never be 0 unless you're at the origin. Therefore, this e has to be the one that's 0. So this implies that e is equal to 0 inside. So we have our first solution. Now for our second solution. E times 4 pi r squared times r hat is equal to q enclosed over epsilon naught. So now we want to find the enclosed charge in this bigger radius, and here we're referring to this r, whereas in this case we're referring to the blue r. So great. The enclosed charge is just equal to enclosed charge over surface density over area is equal to surface density. And we know the area of that circle is just 4 pi r squared, where we're using this r. So we get q enclosed over 4 pi r squared is equal to sigma. Therefore, the enclosed charge in this scenario is equal to sigma times 4 pi r squared. Now, if you wanted to do this thoroughly with some dependence on sigma, you would have to do the same integral, and instead of e, you write sigma. And because sigma, again, is spherically symmetric, because they're giving you a uniform surface charge density, you can bring it outside the equation, and then everything will work out again. But if you're a first year or if you haven't learned multivariable calculus yet, then this is a good enough explanation, and you don't need to go into more detail than that. So writing this out now, we get e times 4 pi r squared times r hat is equal to the enclosed charge, which we have written out here, to be sigma 4 pi big R squared over epsilon naught. Great. So now E is equal to sigma 4 pi R squared over epsilon naught 4 pi R squared 1 over R hat. Great. So now the 4 pi's can cancel out. And we notice that 1 over R hat is the same as R hat, just because it is a unit vector. So, 1 over 1 is equal to 1. So therefore, we can write the final value of E, which is sigma R squared over epsilon naught R squared outside. And you should find that this exactly matches the value that you find in problem 2.7. Great. So thank you very much for watching my video, and I hope to see you again.